Good morning. I'd like to continue talking about the Langlands program and the fundamental lemma today. I gave the outline of the lecture series yesterday. I'll just repeat it here. Yesterday I talked a little bit about the analytic theory and the trace formula. Today I'll be talking about a particular identity on the geometric side of the trace formula. This is called the fundamental lemma. This is a problem that was conjectured back in 1980 by Langlands and then refined with Shellstedt. And it went nearly 30 years without a solution. And this held up progress on the use of the trace formula for many years. So I'll talk a little bit today about Cho's solution to this problem. In contrast to yesterday I was talking about fields of characteristic 0. Today I'm going to move to fields of positive characteristic. If you think of Frankel's lecture yesterday with the various columns, the number fields, and the function fields in positive characteristic, today I'm moving from the first column to the second column. And in the third lecture, I'll be going back and forth between the first column and the second column. And I won't have anything to say about the third and the fourth columns. So let's do a bit of a review. Yesterday, I talked about trace formulas. And these are identities between sums of orbital integrals on one side. So the geometric side these are terms associated with conjugacy classes in the group, and the other side of the formula is associated with representations. And today I'm going to use the notation O for an orbital integral. So whenever you see the O, think of this integral over a conjugacy class. And then last time I mentioned the special case of a trace formula for compact quotients. It takes a particularly nice form of a sum over integrals over conjugacy classes on one side, that's the geometric side, and sums of traces of irreducible representations on the other, and that's called the spectral side. And today we're going to be focused on the geometric side of the trace formula. So we'll be talking about conjugacy classes and integrals over conjugacy classes. And then just the more general version of this, I also mentioned the Arthur-Selberg trace formula. This is where you no longer have a compact quotient, and you're in the situation of a number field where you have a reductive group and the set of points. So the number field is a discrete subgroup of the group of Adels, and you write down a trace formula in that situation. Then I mentioned a little bit about Arthur's proof strategy, and this came down to comparing two different trace formulas, one for GLN, the general linear group, and the other for a symplectic group. And the strategy, as I said, was to pick test functions f and f prime, where you can cancel out a lot of the terms on the left-hand side. So you prove identities between the conjugacy classes, identities between the orbital integrals, and from that you draw information about the relationship of the representations on the two groups. And so I said that we're going to use the fundamental lemma to do this, but today I didn't say anything in detail about this yesterday, and I'm going to go into detail about this today. And then this came up in several talks yesterday. There's a notion of a dual group for any reductive group that you get by exchanging the short and the long roots in the root system. And this dual group governs the representation theory of a given reductive group G. Now, one more slide. There's a variant of the dual where you take a semi-direct product where you take an action of a Galois group on the connected component and form a semi-direct product. So this is the scarce slide. There's a lot of mathematics that comes up in connection with the trace formula and these two columns that Frankel was talking about yesterday and the proof of the fundamental lemma. I understand just a fraction of this. If you're a young graduate student or postdoc, this is a great field to be involved in, to learn a lot of interesting mathematics. You don't have to master all of this to get involved, but it's a very interesting field of mathematics that brings into play many different ideas. So in the middle of this is the fundamental lemma, which is my topic today. Credits for the fundamental lemma. As I said, this went unsolved for nearly 30 years. It was formulated by Langlands in 1980. Refined version was Shellstat. Volz-Bourget was very much involved in cleaning up the statement. And when I say cleaning up, that sounds like an easy task, but this was really a lot of hard research to put it in a cleaner form that was eventually used in the proof. Kottwitz, Goreski, and McPherson became Kottwitz from the very beginning, and Goreski and McPherson around 1990 made very important contributions to the subject. Lemma and Ngo solved the special case of the unitary groups before the general case was done, and there were contributions from many other people as well. But the really key contributions that led to the solution are due to Ngo Bao Cho. So to motivate the fundamental lemma, I'm first going to give an example in representation theory, and then if you believe the idea of the trace formula, things about representations can be transported over to things about representation, over to things about orbital integrals. So I'm going to give an example of a character. So I'm going to take the group of 2 by 2 matrices, a special linear group with coefficients in the real numbers. And these 2 by 2 matrices act on holomorphic functions on the upper half plane by this rule that I've given here. And you get, so you take all those that satisfy this integrability condition, and you get an irreducible representation, just a holomorphic discrete series representation of this special linear group of 2 by 2 matrices. And then there's a similar representation that I won't write down that's very similar, but you use anti-holomorphic rather than holomorphic. And we can take the character of those two representations. And I'm going to, yesterday I was viewing characters mostly as distributions. For the moment, I want to think of this character as a function on the group. And you can calculate the character of these two representations. And what you find is that these two characters are exactly the same, except when you look at a rotation matrix. And when you take a rotation matrix, if you look at the difference, again, they're almost the same, but if you take the difference of these two characters, what you get is this formula that I've given, e to the I n minus 1 theta plus e to the minus I n minus 1 theta divided by e to the I theta minus e to the minus I theta. And if you look at the right-hand side, the numerator on the right-hand side is just the character of a two-dimensional representation of this circle group. And so we have two infinite dimensional representations, and we take their difference, and we get a finite dimensional representation on a smaller group. So this is a really remarkable cancellation property that you have with this character, that you're taking two infinite dimensional representations, you take their difference, and it just collapses to something much simpler than what you had before. And so the general form that we have here is that we have some sort of alternating sum of things, and then we get a character on a smaller group, and they're equal up to some factor, a transfer factor. In this case, it's independent of n. And so what we want to do is find an analogy for this on the other side of the trace formula in terms of conjugacy classes, and we want to express this in full generality. And when we do so, we'll have a statement of what is called the fundamental lemma. The fundamental lemma is, we could think of as most general statement of this form expressed in terms of orbital integrals instead of representations. So to go from this special example to the general case and to use our analogies, we're going to have to do a six-fold generalization of this one example. We're going to replace the group SL2 with a general reductive group. We're going to replace the real numbers with a general, there's a version of this for Archimedean fields, but I'll look at it in particular today for the non-Archimedean local fields. We're going to go to the other side of the trace formula, so we're going to replace characters with orbital integrals. And then continuing, these signs that we had in this character identity, we're going to have to generalize what that means to a general reductive group. This smaller group H that gives the cancellation of the smaller group, we're going to have to describe what that smaller group is in general. There's a name that's been coined for this type of group that holds the cancellation group, and that's called the endoscopic group. There's more than one of them in general for each reductive group. And then we're going to have to replace this denominator by some factor that we get in general. So we do this six-fold generalization and analogy. We're going to end up with a statement that I've written here that I'll make more precise, that we have some linear combination of orbital integrals on a big group, and there's going to be some drastic cancellation caused by the signs, and we get an orbital integral on a much smaller group where a lot of the complexity has disappeared. So that's the general form of the identity that was proved by Ngo-Bao Cho. So to explain a little bit more about the significance of this SL2 example, note that in SL2, clockwise and counterclockwise rotations are not conjugate to each other inside the group. They have the same determinant and the same trace, so they have the same characteristic polynomial, but they're not conjugate to each other in SL2R. To conjugate them, you need to use a complex number to do the conjugation. So they're conjugate inside SL2 over the complex numbers, but they're not conjugate inside SL2R. And this leads to a general definition that will say two elements are stably conjugate if they're regular semi-simple, but the idea is if they become conjugate when you go up to the algebraic closure of the field, but possibly not conjugate down in the ground field. So that's the notion of stable conjugacy, that things become conjugate when you go up to the algebraic closure. If you look, there's a little finite abelian group that governs the set of stable conjugacy classes, set of conjugacy classes inside a stable conjugacy class. Since you're going up to an algebraic closure, you have a Galois group of the algebraic closure over the field. And if you take the element that conjugates one to the other, you can take this expression G times sigma of G inverse, where G is the element that conjugates one element to the other, and sigma is an element of the Galois group. And you find that this gives you a cocycle inside this little cohomology group, where I sub gamma is the centralizer of this element gamma. So this class that you get doesn't depend on the particular choice of element G that you use to conjugate one element to the other. And So when this is a local field, you get a finite abelian group here that we're going to use. And the idea of this, so I gave this example of SL2R where there's this drastic cancellation when you take the right linear combination of things. We have this little finite abelian group. Whenever we have a function on this group, we can just do, this is sort of baby Fourier analysis for a finite abelian group. We can expand a function on this group in terms of the characters on this finite abelian group. And this is what's going to play the role of the signs that we get in the case of SL2R, is these different characters on this finite abelian group. So this is very, very vague at this point, not precise at all, but the rough idea is that you get different Fourier modes for each of these characters, and when you have a particular root system, when you take these particular linear combinations that you get by this character kappa, this little finite abelian group, you get oscillations that are going to cause certain of the roots to become more pronounced and certain of the roots to sort of disappear. And then you get a smaller root system that's going to play the role of the group of rotations in the group SL2R. And so you get a smaller group that is the target for these identities that you prove. Okay, so just recall the basic philosophy of Langlands and the Langlands program. We introduced the dual groups, and the idea is if the dual groups are related, then the representation theory of the two groups should be related. And the simplest way in which the dual groups can be related is if one dual group is actually a subgroup of the other group. In this theory, the subgroups that are centralizers of semi-simple elements play a special role. And the idea of endoscopic group is that the smaller group has a dual that's the centralizer of an element in the dual. So an endoscopic group of a group G is not a subgroup, but if you take the duals of both of them, one is a subgroup of the other. So they're not directly related, but the duals are related. So that's the idea of endoscopy. So this is just formulating this in a definition that I won't talk about in any detail. To formulate more precisely what the fundamental lemma is stating, I want to talk about the characteristic polynomial of a matrix. Okay, so we're all familiar with that notion. That we have any n by n matrix, we can take its characteristic polynomial. I should say that what I'm talking about today is mostly going to be about Lie algebras rather than Lie groups. At the beginning of my lecture, I said that there was a lot of cleaning up of these identities of orbital integrals that was done over the many years during which it wasn't solved. And one of the things that was done was it was shown that these identities, which were originally formulated on a group in terms of orbits there, can be brought down to the level of the Lie algebra and formulated in terms of the Lie algebra. So I'm not going to show you exactly how that reduction is done. That's part of the cleaning up that was done. And so in today's lecture, I'll mostly be talking about orbital integrals in the Lie algebra. So you can take conjugacy classes in the same way in the Lie algebra as you do in the group. And it's just a little easier to formulate and prove in that context. So instead of taking GLN, I'm going to take all n by n matrices, the Lie algebra of GLN, and we can take its characteristic polynomial. And I want to think of the characteristic polynomial of a matrix as a map from the matrix to the collection of coefficients. of the matrix. So I'm going to forget about the polynomial and just look at the coefficients of the polynomial. And in that way, I formulate it as a morphism from the Lie algebra, in this case, Lie algebra of GLN, into the collection of coefficients, which will be an affine space. And Chevalley worked out the generalization of this from the general linear case to a general Lie algebra. You can take the Lie algebra and the action, the adjoint action of the group on the algebra and take the invariance. And this is the same as, we've got this identity that I've shown in the middle. I can take a Cartan and the invariance under the Weil group, and then I can take spec of that algebra and I get an affine space. And the generalization of the characteristic polynomial or the characteristic map is just this map determined by Chevalley's theorem. And so we have a way of talking about the characteristic polynomial or the characteristic map now for a general Lie algebra. And what you find is that two regular elements, gamma and gamma prime, are stably conjugate in the sense that I talked about earlier. They become conjugate over the algebraic closure if and only if they have the same image down in this, if they have the same characteristic polynomial. So now I'm going to talk about the identities that come up in the statement of these identities of orbital integrals. We'll take, like I say, today's talk is going to be for function fields, we'll be talking about positive characteristic. So for the moment, I'll take a finite field, a non-Archimedean local field containing that field, and the integers, and then I'll take, so this C is representing the space of characteristic polynomials. So if I pick an A in there, I think of fixing the characteristic polynomial. So I'm fixing the stable conjugacy class of the element. And then if we jump down to this identity, I'm taking a sum over all of the conjugacy classes inside the stable conjugacy class. I'm taking their orbital integrals. So this is the type of thing that shows up in the trace formula. And then this kappa applied to gamma, this is the little finite group Fourier analysis that we're doing. These are the signs that came up in the SL2 example. We're taking linear combinations weighted by different signs. So since we can expand any function in terms of its Fourier expansion, any combination of orbital integrals can be expanded in terms of integrals like this as we run over the various characters kappa. This is just a finite group Fourier expansion. So we can always make an expansion like this. And this is then the analog of the left-hand side of this equation I've shown. I've repeated it down at the bottom right, this identity of characters that I showed at the beginning. Instead of a linear combination of characters, we now have a linear combination on the geometric side. And what we want to do now is to relate this to a right-hand side where all of the signs are now positive, but we're now on a much smaller group than before. So that's the strategy. And so here, when I write SO, instead of O sub k, I just mean all of the signs are positive. So we're taking kappa to be the trivial character. And so that's the linear combination that we're going to have on the endoscopic side, on the smaller group. And so the idea then is to have a linear combination of orbital integrals related by a kappa on the left-hand side and something that's a stable orbital integral on the right-hand side. And this is then the statement of the theorem that was proved by Ngo-Bao Cho, is that this kappa, this linear combination with signs of orbital integrals on the group G, we can relate the characteristic polynomials of the element on G and the characteristic polynomial on this smaller group H. And then on the one side, we take this linear combination with signs, and we get a big cancellation, and we drop down to orbital integrals on this much smaller group, but now without any signs, so all of the signs are positive. And we get an equality up to what's called the transfer factor, and in this case, it's just some power of q. So that is the statement of the theorem that went many years without a proof, finally proved in 2010. For this work, he was awarded a Fields Medal. It's a very deep and difficult theorem to prove this. But this was the missing ingredient on the trace formula that was holding up progress for many, many years. And I don't think I'll have time to talk about applications today. I talked about Arthur's work last time as one application. If I have time tomorrow, I'll mention a few other applications of the trace formula that are based on this identity. So this is the key identity between orbital integrals that's needed for a comparison of the trace formulas for G and H. The fundamental lemma makes it possible to extract relationships between the representations of H and representations of G. This is using the trace formula going back and forth between identities of conjugacy classes to identities between representations. Okay, so in the early days, let's now go back to early 1980s. How did people try to prove the fundamental lemma? Well, if you look at this orbital integral, we're taking the characteristic function of the Lie algebra with coefficients in the ring. And from the fact that what function that we're using here, if I replace this element G by anything in this coset, this add G inverse doesn't change. And so the number of G's, the set of that we're integrating over G is depending just on the set of cosets. So you can actually turn this integral into a sum where you're summing over the number of cosets that are inside that satisfy this support condition. So it looks like you're doing an integral, but because of this coset interpretation, you can just count the number of cosets that satisfy this identity with the right measure. And so you can try to view this as a combinatorial identity. Let's just do a coset counting problem on both sides. We have, if we have an elliptic element, we have a finite number of cosets on one side and a finite number of cosets on the other. Let's just do the combinatorics and compute it. So this was done in simple cases, like groups of rank 1, using the building and so forth. And you get these combinatorial identities in Q, the number of elements in the residue field, for both sides. And you do this hard combinatorial calculation on one side, a hard combinatorial calculation on the other side. You say, okay, the fundamental lemma holds in this particular case because we computed both sides and they're equal. But there was really no insight about why you should always get the same answer when you do these calculations. You just do one hard calculation, another hard calculation, and you'd find it always works. So this was convincing evidence, but hardly a way to go about proving it in general. So a really key development came in 1988 with Kazhdan and Lustig, where they found that this counting points, if you do it over the algebraic closure of your finite field, this is precisely equal to the number of points on an n-scheme called the affine Springer fiber. So now we're starting to see a little bit of geometry coming into the calculations. And there was an appendix by Bernstein to this paper that does a calculation in the symplectic group of rank 3, just doing a particular calculation for a particular element gamma inside this particular group. And what you find is that you get an elliptic curve for the number of, so you're counting the number of points on an elliptic curve here for the, he did it in terms of characters, but you can do the same thing in terms of orbital integrals. And so you really see that there's going to be some geometry involved in finding a solution to these identities of orbital integrals. So let me just do a calculation. This is a calculation that I did back in 1992. So this still goes way back. It was just a few years after this paper by Kazhdan and Lustig. But I'll take the Lie algebra. I'm doing everything in terms of the Lie algebra today. So I'll take the Lie algebra SO5. I'll take an element, and I'll just count its, do a calculation of the orbital integrals for this group. And the relevant thing is the bottom line here is when you calculate the orbital integrals for suitable test functions, what you find is that there are rational functions a and b that come in, but there's also the number of points on an elliptic curve over a finite field where that elliptic curve is being determined by this element A. So the J invariant of this elliptic curve is depending on the element. And then when you try to, so then you've got some identity that you want to prove between the two sides. You've got an elliptic curve on one side. Well, you better find an elliptic curve or something similar on the other side. Now, the easiest thing would be if you just got the same elliptic curve on the same side, and then you would have your identity, and you'd be able to prove this case of the fundamental lemma. But what you find is that you get different elliptic curves. They have different J invariants. And the identities that you need to prove between the two sides consist in finding an isogeny between the elliptic curve on one side and the elliptic curve on the other side. And so the geometric content of the fundamental lemma is proving the isogeny of elliptic curves. So in yesterday's lecture it was all the analytic theory, but here we've written down terms in the trace formula and the calculations that we need to do. We see that we're forced to do geometry to understand the solution of the fundamental lemma. Okay, so this was known way back. Okay, so this is just the statement of the isogeny. You do similar calculations in higher rank, and you get hyperelliptic curves coming up when you compute these integrals. So then starting, this was starting I think around 1990, Goreski, Kotwitz, and McPherson made very extensive investigations of these varieties, the affine Springer fibers. And based on their investigations, they made a conjecture that the cohomology groups of these affine Springer fibers are pure. And assuming this conjecture, they're able to prove the fundamental lemma not in the general case, but at least in a special case when you take elements whose centralizer is an unramified Cartan subgroup. And just by direct calculation in particular cases, they were able to prove this purity result in some special cases that gave some evidence to this conjecture. But they weren't able to prove the fundamental lemma in general, and they weren't able to prove the purity conjecture in general. And Lemma made a systematic investigation of the affine Springer fibers in the case of unitary groups, and Ngo-Bao-Cho became involved in that, and together they were able to give a complete proof of the fundamental lemma for unitary groups based on the geometry of the affine Springer fibers. But from all of this research over the years, Ngo realized that there were sort of two big problems that you needed to overcome to prove the fundamental lemma in general. First of all, the unitary group, if you look at its endoscopic groups, over a quadratic extension, the unitary group just becomes GLN, and the endoscopic groups just become Levy factors of GLN. And coming from the center of this levy, you get an action of a torus acting on the situation that is sort of a special feature of the unitary group, that you don't have in general. And they use this torus action in a very important way in their proof of the fundamental lemma. And he realized that he wouldn't be able to use this in general. And the second thing was this purity issue. So this work by Kotwitz, Goreski, and McPherson, they needed this purity result, but they were having a hard time proving it. And just based on Deline's work, Ngo had the idea that maybe if you put these affine Springer fibers into families, you would have better luck in trying to establish the purity results that you need in families rather than just an individual fiber. And so we're talking about column 2, we're talking about smooth projective curves and function fields in today's lecture. So what he did is he said what happens if we vary these affine Springer fibers over a smooth projective curve. And when he did so, he found that instead of looking locally at a particular place, we now have something global, and he found that the global analog of these affine Springer fibers was precisely the Hitchin fibration. And this was really a key point in the, if you were in Schiffman's lecture, we learned a little bit about the Hitchin fibration. This comes up in a very important way in the proof of the fundamental lemma. And so just, I have one slide I want to compare with what was done yesterday. Schiffman described a stack of Higgs bundles and the Hitchin map. Ngo-Bao-Cho's proof of the fundamental lemma is based on this Hitchin map for a general reductive group. But there are a couple of mild changes from the setup from yesterday. We need to do this for a general reductive group. So a Higgs pair is now, we'll take a torsor on our smooth projective curve X. So I'll use the same notation X for the curve that we're talking about. And then a section of, if we have a torsor, we have an adjoint action of the group on the Lie algebra. There's an associated bundle that we can take, and we take a section of that bundle, and such pairs are the Higgs pairs. We're tensoring all this with a line bundle. This is the one difference from yesterday, is that we're taking a general line bundle here today, and that causes a few changes. So yesterday you had a completely integrable system. It was symplectic, and the Hitchin map was Lagrangian. Those properties no longer hold when we take now a general line bundle. But other than that, we're pretty much in the same situation as yesterday. So here's the picture. We have a smooth projective curve. We have these Higgs pairs, and then each Higgs pair becomes a point in the moduli space of all Higgs pairs. And if we look on the left, this phi is something, and each fiber is something in the Lie algebra. And if I have something in the Lie algebra, we can take its characteristic polynomial in the sense that we did in an earlier slide. So fiber by fiber, I can take a characteristic polynomial, and then I can vary that as I go from fiber to fiber, and I put those together. I get a section over X with values in this space of characteristic polynomials. And this is just the Hitchin map. So we're just fiber by fiber taking the characteristic polynomial, and that is the map from the total space of Higgs pairs down to the base. And so when I fix a point down below, I'm really fixing the characteristic polynomial. I'm fixing the stable conjugacy class of something. And so the starting point for Ngo-Bao-Cho in the proof of the fundamental lemma is that for each line bundle D, there's an explicit test function that you can pick that with the property that at least for anisotropic elements in the base of the Hitchin fibration, that corresponds to a characteristic polynomial. So I can look in the trace formula and look at the terms in the trace formula that correspond to that element A. But I can also look at the Hitchin fibration, look at the fiber in the Hitchin fibration over that element A, and count the number of points. And this is sort of the stacky way of counting points that was talked about yesterday, where you need to count points weighted according to symmetries. And if you count the number of points in the fiber, you get it precisely the terms in the trace formula corresponding to that conjugacy class. Okay, so everything was analytic yesterday, but the terms in the trace formula, those numbers for this particular test function are precisely equal to the number of points in the fiber of the Hitchin fibration. So what this sets up is sort of a program that you can do. You can look at all of Arthur's papers, for instance, on the trace formula and how he manipulates the terms analytically. And then you say, well, let's do this all geometrically, because we've now got this correspondence between points on this stack and these orbital integrals. And so the manipulation of terms, in general, the stabilization, we talked about stable conjugacy classes, the manipulation of terms where you put all of the terms according to a given kappa, to a given character, this little finite abelian group, when you arrange those so those terms are all together, that's called the stabilization of the trace formula. And what you find then is, so this is done in a paper by Cho, that there's sort of a parallel thing that you can do with the Hitchin geometrically, with the Hitchin fibration, where you do stabilization. So stabilization, I don't mean it in the sense of stable bundles, but now we're talking about stabilization of the trace formula. You can do a parallel thing on that side. So there was a discussion yesterday about Hitchin fibration, so I won't repeat it. So let me just say what a few of the key ideas of the proof, the fundamental lemma, were. So this was proof is not short. The proof is something like 170 pages to give the proof of the fundamental lemma in full generality. But the first key idea I've mentioned already, that this Hitchin fibration is the global analog of the affine Springer fiber, so that terms in the Arthur-Selberg trace formula can be interpreted in terms of the Hitchin fibration. Second key idea, I'll come back to each of these points. The Hitchin fibration carries a large symmetry group that's very well suited. So it's very difficult to pass information from the group over to the endoscopic group because they're not directly related. Only their dual groups are related. But there's a large symmetry group that you can pass back and forth between the group and the symmetry group, and that gets used to great effect. A third key idea is that you can use continuity arguments. Once you go to the global situation, you can prove the fundamental lemma in some rather simple situations and then pass to a limit and get the fundamental lemma in much more difficult settings. And then finally, there was this issue of purity that came up in the work of Kotwitz, Goretzky, and McPherson, and that can be taken care of globally with the notion of pure perverse sheaves. So local to global correspondence, I've talked about this a little bit already, but you've got the affine Springer fibers locally, and if you look at their descriptions in terms of torsors and stacks, there's an analogy between how to describe these two objects, and in fact Cho proves an identity, an equivalence of categories, that you can take a product on the left-hand side and relate it precisely to something on the right-hand side. And this is sort of geometric analog of what we're doing with the Adels yesterday. That was a restricted product of over all of the places of the various completions. So I just make this point down at the bottom. Many people believe that a global argument would not work because, see, the trace formula, the Arthur-Selberg trace formula, is already a global thing. This is something for the Adels. And then you take these global identities that you want, and then you express these key identities that you need as p-adically as these local identities that you need. And so then it just seemed to be going in circles to go back to a global situation again. But it's a different global situation that you're constructing that allows you to bypass the trace formula difficulties and do it. Well, okay, so it works. So Langlands and his Shaw Prize. I just want to read. I also had occasion to listen to lectures of Ngo. In particular, I had to attach for myself some meaning to the notion of stack and the algebraic stack. It was a revelation. I discovered I had been thinking for decades of orbital integrals in an incorrect way. I had separated the local from a global part. So the second key idea that I mentioned was symmetries of the Hitchin fibration. I'll just briefly indicate the idea for in terms of GLN. If I take a point, so we have a surface, and for each point on that surface, we're fixing an element A, which is like the characteristic polynomial. And so for each point on my smooth projective curve, or Riemann surface, if you want to think of it geometrically, I've got that characteristic polynomial, and the roots of that polynomial give finitely many points over each point on my smooth projective curve. So what I get is a cover of my original curve corresponding to the eigenvalues of that characteristic polynomial. Okay, so I get a cover of the curve corresponding to the eigenvalues. And the the Higgs pair gives an endomorphism so that has that characteristic polynomial. And so that endomorphism, for a given eigenvalue, I can pick out if things are sufficiently regular, that'll be a one-dimensional eigenspace, and I can pick out a line for every point on that covering space. So I have this covering curve that I denote by YA, that's the spectral curve, and for every point on that corresponds to an eigenvalue. I can pick a one-dimensional eigenspace that corresponds to a line, and then as I vary the point, I get a line bundle on the spectral curve. And so I get an element of the Picard group, and as well known, the Picard group is related to abelian varieties, and you start to see how these earlier calculations, why something like an elliptic curve might have come up in the calculation of the orbital integrals. And in general, you get a group of symmetries coming from a Picard stack acting fiber by fiber on the Hitchin fibration. And these symmetries are coming from this centralizer, I sub gamma. So we have a semi-simple element, we can take its centralizer. So these symmetries are coming from the centralizer, and the centralizers are the same for the group and for the endoscopic group. And so we can pass this information about centralizers back and forth between the group and the endoscopic group. So it's always a good idea to use symmetries when studying something, but in this case there are particularly good reasons to study symmetries, and that is that these symmetry groups pass back and forth between the group and the endoscopic group. So whatever information we can encode in terms of the symmetry group is information that we can pass between the two sides of the identities that we're trying to prove. Okay, so that's basically just what I said. The Picard groups on the group and the endoscopic groups are directly related, so that information passes back and forth. So the third key idea is continuity. So if you look back at the early calculations by Langlands and Shellstad, if you take an orbital integral of a regular semi-simple element and you look at the behavior as that element varies, as you tend towards the identity element in the group or the zero element in the Lie algebra, those integrals are getting more and more complicated as you're tending towards zero. And well, Langlands, and this is what I did in my thesis, we sort of worked out some asymptotic expansions as you're tending towards the identity to see what the behavior of these things look like. But the fact is that these are getting very complicated as you're tending towards hyperplanes or towards the identity. And the idea is to completely bypass those difficulties. If you're looking locally, you can't really get around it. But when you look at it globally, so on the right I'm showing an intersection, this curve coming back to itself, meeting itself. I'm trying to illustrate there a self-intersection with high multiplicity there. That corresponds at that one particular place of something that is going to be corresponding to something that will be difficult to calculate in terms of the orbital integrals and so forth. But if I take a slight deformation, then I can arrange for the intersections to be transverse. And this is going to be, and you can't do this locally, you can't do this just at one place, but when you're looking at things globally, you can take this deformation and so the justification of this continuity principle is the deepest part of his work, but in the end, he only has to calculate very simple orbital integrals. So he does very, very simple calculations, and these identity, and then he shows that these identities hold on an open set of the set of parameters, and then by continuity, they have to hold in general. So no hard calculations, direct calculations of orbital integrals are involved. But to justify the calculation, the BBDG decomposition is required, and this is also related to the purity results that I stated. But globally, the number of points, the orbital integrals are given by the number of points on the Hitchin fibration. This number is computed as a perverse sheaf, and the geometric form of the fundamental lemma becomes an identity of the equality of the semi-simplification of two different perverse sheaves. And they have a common base space. And so on an open set of this base space, you can do the calculations, and as I said, this is sort of staying away from these difficult calculations. So it's a relatively easy direct calculation. So that can be used to show that the semi-simplification of these perverse sheaves are equal on this open set. However, two perverse sheaves can be equal on a dense open without being equal. What you need to do is prove some results about the support of these perverse sheaves. And this is really the most difficult part of the proof, is justifying results about the support of these sheaves. So by the BBDG decomposition theorem, if Z is closed and irreducible, and if two simple perverse sheaves have support on Z and they're equal on a dense open, then by this result, then they're equal on all of Z. And so what you need is results about the support. And the support theorem breaks into two parts. Each support z of every simple geometric factor also appears in the support of some factor in the ordinary cohomology of top degree. And second, the supports in the top degree ordinary cohomology are as large as possible. So he has to prove results about supports. The strategy is to take some piece of cohomology and you want to prove something about the supports. You have these symmetries by abelian varieties, and he uses cup product operations with the abelian varieties to push the cohomology up into the top degree. And once it's in the top degree, he gets an explicit description of the cohomology in top degree using this group of symmetries. And once it's expressed in terms of the group of symmetries, I said this is something that passes back and forth between the two groups. So this, like I say, is the most technical, difficult part of the proof. But in the end, he is able to justify these support conditions that you need to justify the continuity argument that he uses in the proof. This is Langlands again, an exposition of the fundamental lemma, generally accessible not alone to someone of my generation, but to mathematicians of all ages eager to contribute to the arithmetic theory of automorphic representations, would be close to 700 pages. So I certainly haven't done justice to it today, but at least I've hoped to have given some indication how geometric representation theory was not only useful but rather quite indispensable in proving these results about orbital integrals that come up analytically and in terms of number fields in the trace formula. Now today I've talked about the proof of the fundamental lemma. This is all in positive characteristic. To go back and to apply this to number fields, you have to transport these identities from positive characteristic back to characteristic 0. And that's going to be the topic of my third lecture, how it is that, so we've used geometry here, the geometry of the Hitchin fibration, in proving the fundamental lemma in positive characteristic. In characteristic 0, you don't have any of this geometry to use, but you still need to know the fundamental lemma. And so I'll talk tomorrow about how that is done. Thank you.